So we're talking about complements and substitutes. So this is probably some words that you've heard in an economics class at some point, or a variety of different economics classes at some point. The idea that certain goods have a relationship to each other, that they either, complement one another or are substitutes for one another. In other words, they're either consumed in tandem or they're consumed in place of each other. We talked a little bit about this um, when we discussed the indifference curves of different kinds of utility functions, and we called some perfect complements and perfect substitutes, and those are sort of the extreme cases of these two. So the idea of formalizing this, or towards formalizing it, we think about how the change in demand, how the demand for xi changes as a function of the price, not of this itself, but the price of a different good. So we've thought about already how does xi change when you change the price of good I, right? And it can go up or down in terms of Walrasian demand. Almost always it goes down, right? If the price goes up, you consume less. But we had these particular cases of Giffen goods. We can't rule out the potential that the price of a good could increase and the demand could simultaneously increase. Now what we're interested in is does the demand, so one other thing, obviously in the Hicksian case, right, we have the law of compensated demand, which says if the price of a good goes up, the amount of that good demanded in an expenditure minimization problem decreases, right? Because in the expenditure minimization problem, we only have substitution effects and not an income effect. That's the idea of compensated demand, is that you're compensated for price changes, so there's no income effect. If the ratio of prices changes, you're not going to be richer or poorer. Whereas in a Walrasian case, when the prices change, that actually changes what is a feasible bundle, right? That changes what budget set you're facing. So that's just a little recap. What we're going to talk about in this lecture is the idea of a price change with respect to a different good, right? So how does the demand for xi change when the price of pj goes up or down? Now, we introduced this idea of Slutsky decomposition, which was this horrendous looking equation with tons and tons of different letters appearing in it. And admittedly, when you look at that, you could think, there's not much there for me, and that's fine. But it still works here, right? So the change in Walrasian demand with respect to the change in price of a different good is given by the change in the Hicksian demand with respect to that different price, minus the change in income that's relative to how much of good J you were buying times the change in the price of good J, right? Which is equals a change in income, right? Because if I'm buying a lot of good J and the price goes down, I'm relatively more wealthy. So this still works, and if you're trying to calculate the change in a Walrasian demand, you can still do this, and you can still analyze things in terms of this equation. That's not what we're going to do today. So what we are going to talk about is how changes in a price are really changes in the price of its own good are movements along a demand curve. So I don't know if you remember from an intro economics class, you have things that change the movements along a demand curve and shifts of the demand curve, right? So changes in other goods prices shift the demand curve. It creates a completely new demand curve, right? Because xi star of I is a function, the demand curve for good I is a function of the price of good I alone. It fixes all the other prices. So when we change the other parameters, the prices of other goods or the income, that's actually changing the entire function. So along every price along every price point for good I, we have a new demand potentially a new demand because of the change in the price of a different good. So that's a complete shift of the income curve, of the demand curve. Now, really what we're interested in is, as betrayed by the title of this lecture, is there's a difference between complements and substitutes. Complements we could think of as being movements in tandem, right? When I consume more of X, I want to consume more of Y. And substitutes, when I consume more of X, I want to consume less of Y, right? So a complement is something that goes together, so I want to consume them at the same time, and a substitute is something that I would consume one or the other, so I'd want to consume them at different, one or the other. So we can look at what this looks like graphically, right? So on the in figure A, we have a scenario of gross complements. So what's happening? We start at the budget set I0. right? I0 is an original price for X and a price for Y. Now, we're going to move from the budget set I0 to the budget set I1. Income 1 is what happens when the price of good Y falls, right? We're moving up, we're able to afford more Y. So the price of Y has gone down, and we've moved from the smaller budget set to the larger budget set. In doing this, we haven't changed the price of X at all, right? The intercept on the X-axis remains the same. If all you're doing is buying X, you can buy the same amount. The price of X has not changed. So the only thing that we've changed in moving from I0 to I1 is the price of good Y. And in this case, the price of good Y has gone down. Now, we look for what is the Walrasian demand in these two cases, right? So we first find the Walrasian demand in the first scenario, and then we find the Walrasian demand in the second scenario. They're nice interior solutions. They're given by the tangency of their indifference curves. And we find that at I0, when the budget set is I0, the Walrasian demand is given by X0, Y0, and it lies on this utility curve, U0. This utility curve, this indifference curve, is the point of tangency. There's nothing special about it. We move now to the higher budget set, the larger budget set, where we've decreased the price of Y, and so now more things are affordable than they were before. And we see that here we lie on a new indifference curve, U1, and the point is that Y has increased. The consumption of Y has increased, right? So Y1 is higher than Y0. And that's sort of intuitive because the price of Y has decreased, and so I'm going to increase my consumption of Y. That's not guaranteed. Of course, we have given goods, but most of the time we're going to see a price drop in Y, an increase in consumption of Y. So the price of Y falls, the consumption of Y increases. All that's good. We already know, we've already analyzed that in the last lectures. What we're interested in now is how does this price drop affect my consumption of X? And here we see that X1 is larger than X0. So because the price of Y has gone down, I end up consuming more X1. And these would be called complements, right? So the idea is that I want to consume X and Y at the same time. These are complements, they complement each other, they reinforce each other, right? So perfect complements would be something like left shoes and right shoes. Something that you have to consume them exactly in a pair. And when you have to exactly consume something in a pair, if the price of one goes down, you can now afford more pairs. But that means that you're consuming more left shoes and more right shoes. So, right, when the price of left shoes falls, this gives you more income because you can afford, you were spending however much on pairs of left and right shoes. Now you have a little bit of extra money because the price of the left shoe fell. You're going to spend that money not only on left shoes, but also on right shoes because to get more utility out of that extra income, you have to buy an entire pair or a unit of shoes. So you move from a point where you've consumed a little bit of Y and a little bit of X to a new point where you consume both more Y and more X, right? And the idea is that you're consuming both of these at the same time. So a movement, an increase in the consumption of Y corresponds to a desire to consume more X. Having more left shoes makes right shoes more valuable. And if left shoes are cheaper, I can afford more of them. I want more right shoes to go along with them. Now we're going to compare that scenario to what's happening in the panel B. In panel B, the setup is the same. We started out at a smaller budget set I0. We decreased the price of Y to get to I1. In this movement, you can see that, again, the consumption of Y has increased. So Y1 is higher than Y0. I increase my consumption of the good that becomes cheaper. The difference here is that X1 is now less than X0. So I've decreased my consumption of X. So in consuming more Y, I end up consuming less X. And these are called substitutes. I'm changing my consumption away from X towards Y. Now, when are something substitutes? When they approximately enter your utility function in the same way. When they don't need to be consumed in tandem, but rather you can choose between either one of them and get the same value. So something like this might be the price of apples and the price of pears. If I like apples and pears approximately equally, I don't really think too much about which one I want. I don't care how much of them I have. They're substitutes for one another. Then when the price of pears falls, I'm going to eat more pears. And by eating more pears, I've reduced my desire for apples because I don't need the apples. I have pears instead. So unlike the case of complements, where when one good falls, I want more. When the price of one good falls, I want more of both of them. Here, one good falls, I want more of the one that's cheaper, and I substitute away from the one that's more expensive, relatively more expensive, right? The one where the price remained the same. And so these are, I think, relatively intuitive, and you can kind of think through the logic of it. If you want to consume these things together, then when one gets cheaper, you want to buy more of both. If you want to consume one or the other, when one gets cheaper, you want to just consume the cheaper one and move away from consuming the more expensive one, since it does the same thing for you, but now it's relatively more expensive. So we can look at the examples that are kind of running through the class of perfect complements and perfect substitutes. Perfect complements, we have this minimum function. You have to consume x and y at the same time. That's like the left shoes and the right shoes example. Perfect substitutes, you can either consume x or consume y, and they give you the same utility, and that would be like apples and pears, or tea and coffee, or something like that. Or, red-colored beads and blue-colored beads, if you're colorblind, right? So whatever. There's plenty of examples. The idea is you should be able to now, at this point, graph these indifference curves, look at a change in a budget set, and convince yourself that the things that we're holding on the previous slide are holding for these particular utility functions. That you see with the perfect complements case, you see a co-movement of x and y. When y gets cheaper, it increases the value of x with this minimum function. And with substitutes, you should be able to convince yourself by drawing the indifference curves that you see a movement away from the relatively more expensive good. We want to make this formal. Formal in the sense of we want to give a mathematical interpretation to it that's more than just having to graph it all the time. So we're gonna call goods I and j, two goods I and j, gross complements if the derivative of the Walrasian demand with respect to good I, with respect to the price of good j is less than 0. Right? So something is a complement if when the price of good j goes up, I consume less I, right? So they're moving in the same direction. When the price of good j falls, I want more. When the price of good j falls, I want more j and more I, right? So the demand for I is increasing. Here, the derivative, when the price of good j goes up, I want less j and less I. So I want them both to be less, right? And so the derivative of xi with respect to pj is less than 0. That's a complement. That means that I find the price changes when the price of j goes up, it makes x less desirable, right? Because it's making j less desirable, it's also making I less desirable. The opposite is true if the derivative of xi with respect to pj is greater than 0. Then we call these things gross substitutes. When the price of good j increases, I end up consuming more I, right? If I consume more I, that means I'm substituting away from j towards I. J became less desirable because the price increased, and I've increased my consumption of I in response to that, which means I'm using I as a substitute for j because j became less desirable. We can also define the same definitions using the Hicksian demand rather than the Walrasian demand, and then we call these things net complements and net substitutes. So something is a net complement if the derivative of hi with respect to pj is less than 0, and the derivative of hi with respect to pj greater than 0 means it's a net substitute. And the intuition is the same. The intuition behind the definition is the same. And so we can think about this from either the Walrasian utility maximization perspective or from the expenditure minimization Hicksian perspective. So the idea of gross complements and substitutes is certainly a more intuitive definition. It's more intuitive just because we generally think of utility maximization with respect to a budget as the more intuitive way that people make decisions, right? We're not generally trying to hit some happiness target and minimize our expenditure. We walk into a store with money and we think about what's the best thing I can buy with this money. So the Walrasian paradigm seems more in line with the way that people behave, and so it seems more intuitive to think, if the price of apples increases, do I buy more or less pears when I'm maximizing my utility with respect to the same budget, right? That's sort of an intuitive notion of complements and substitutes, whereas do I buy more apples or when the price of pears increases? Um, when I'm trying to minimize my expenditure relative to some utility target, just seems slightly more foreign, right? So the idea of gross complements and substitutes seems a bit more intuitive to me, maybe to everybody, but definitely to me, than the idea of net complements or substitutes. Um, but there's a problem with gross complements and substitutes, and it's that it's not symmetric. And so here's an example. We're going to do a little example. So a consumer has a utility function given by the utility is given by the log of x plus y. So it's two goods, x and y, and it's the log of x plus y. And she's got a wealth of I and faces prices px and py. So we can then ask the question: are these goods complements or substitutes? And so we can go through this. Let's go through this. Numerically. So we start out with the idea we'll write down our utility function, our utility of x and y is equal to ln x plus y. And we're going to try to find out if it's a net complement or gross complement or substitute. And something being a gross complement or substitute, of course, means that we have to find the Walrasian demands for the two goods. And so how do we find the Walrasian demand for goods? We have to set up the Lagrangian and solve it. This is a nice differentiable utility function. So I think using the Lagrangian method makes sense here. So the Lagrangian is just ln x plus y minus lambda px x plus py y minus I. And then we have Lx is the first order condition with respect to x. So the derivative of ln x is 1 over x. The derivative of x over here gets us a negative lambda px. And that's going to be equal to 0, which is another way of saying that 1 over x equals lambda px. And then we can write down our first order condition for y. The derivative of y with respect to itself is just a 1. And then we have a lambda py equals 0. And that implies that 1 is equal to lambda py. And then finally, of course, we have our Lagrange multiplier additional first order condition. So now we look in lambda. And we can write that as just budget constraint again, which is just that pxx minus pyy is equal to I. Now, what do? Take the derivative with respect to, take the ratio of the Lx and Ly, and we end up with we get that 1 over x is equal to px over py, or that x px, right, so this is just dividing these two by each other, and then we can just multiply each side by x and py, and we get that py is equal to x times px, which implies that x star, so that already gives us a solution for x star, so x star is equal to, that looks like py divided by px. Right, so we can find that that's a solution. Of course, there's constraints here on if py and px are big enough, are different enough such that x star is larger than the cost of this would be larger than I, then we have a problem, right? So you could run into a boundary condition where you're spending all your income on x, and in which case you'd be consuming 0 y. But we're going to assume we have a nice interior solution. So py and px are relatively close, so that this is smaller than I. And then to find y star, we have to plug this equation back into this, right? So if we plug that in for x, right, we have x px over on this side, and so we can replace that with a py. So py is equal to x px. We have an x px, so we can use this equation, and we can get that y minus, that's a plus, y plus py, y is equal to I, right? In other words, y star is equal to I minus py, this is py, right? I'm plugging in py is equal to xpx. So I get a py plus pyy is equal to I. And that means that I minus py divided by py. Right? I just subtracted the py onto the other side and then divided the whole thing by py, and I get that y star is equal to I py minus py over py. And so this is my value for x star, and this is my value for y star. And you can check that as long as these things are positive, they're both positive. What does it mean for them to both be positive? It means that py has to be less than I, right? As long as py is less than I, then y star is positive, x star is positive, and we're going to, you can plug that into the budget constraint. You can see that this does in fact satisfy Walras' law, that you're going to spend your entire income, blah, blah, blah. Now, what's interesting here, right? Let's look, are these things gross complements or gross substitutes? So remember that gross complement says we have to take the derivative of x star with respect to py. So we're going to take dx star with respect to py. This is x star. When I'm writing x star here, I don't mean the Walrasian demand as a vector. I mean the Walrasian demand of the x component, right? I'm talking specifically here about the x dimension of Walrasian demand. I know that the notation is a little bit overloaded. That's just something that happens in economics. We use x to mean a lot of different things. So x, in the lecture notes, a bold-faced x is, of course, the Walrasian demand. This would be a flat-faced x, a thin x, and that would mean that it's x, the x component of consumption. So this is the derivative of the x component of consumption with respect to the price of y. And what is that? Well, it's just dx star dpy, which is just 1 over px, right? So it's just this divided, this is just py times 1 over x, so that's just 1 over px, which is greater than 0, right? 1 over px is greater than 0 because px is greater than 0. We know that prices are strictly positive. I mean, or we're assuming prices are strictly positive, and so 1 over a positive amount is a positive amount. And what about d? So what does this say, right? This says that when the price of py increases, I want to buy less. I want to buy more x star. But when the price of py increases, I want to buy more x star. Which says that they are complements, right? No, substitutes, sorry. When the price of py increases, I want to buy more x, they're substitutes, right? I'm substituting away from more expensive y to get more x. So this says gross substitutes. And theoretically, you should say we're done here. If y is a substitute for x, then surely x is a substitute for y, right? And the problem is we can take the derivative of y star with respect to px, and we get a 0, right? X does not show up anywhere in the expression for y star. And this says they're not anything. They're not either substitutes or complements. That's problematic, right? So it's problematic. We've now come up with a scenario where we have an asymmetry between the complements or substitutes of these goods. So we can go through the thing. I go through the example also in the slides, but the takeaway is that complements and substitutes in the gross scenario, when we're talking about Walrasian demand, are not symmetric notions. You can talk about if x is a complement or a substitute for y, and that does not tell you anything about if y is a complement or substitute for x. And that's a very unintuitive thing, right? It's kind of hard to understand what that even means. In this case, we got gross substitutes and a neutral thing. I think you can cook up examples where they're opposites. One's a substitute, one's a complement, but it's going to be a much uglier utility function. You might have to have more than 2 goods. And don't hold me to that. But the point is that there's something kind of unsatisfying about that. And it's related in all the same ways that we had these Giffen goods and all this other stuff to this sort of odd character of not really being able to express the way that Walrasian demand changes with changes in price. Well, raising demand is sort of a wild child when it comes to changes in price, right? And the reason is that you're not compensated. There's these two different effects. One is an income effect and one is a substitution effect, and they can go in wildly different directions. And so it's very hard to pin down exactly what's happening. Just as we had a law of compensated demand, net substitutes, the Hicksian demand is much more well behaved, right? And so you kind of swallow the unintuitive part of it, and that's the cost, and the benefit you get for taking that unintuitive expenditure minimization route is that you get much nicer theorems, right? And so net substitutes are symmetric. And this is because we know that the Hicksian demand is the derivative of the expenditure function. So if you remember back to our lecture on duality and the lecture on Hicksian demand, we had a theorem that said the Hicksian demand is the first derivative of the expenditure function. So if the Hicksian demand is the first derivative of the expenditure function, then the derivative of the Hicksian demand is the second derivative, the cross partial, right? That's how we proved the law of compensating demand, remember, because the expenditure function was concave and the second derivative therefore was greater than 0. That's the second derivative with respect to the same price. Now we're talking about the second derivative, first the derivative with respect to pi, then the derivative with respect to pj. Well, cross partials are symmetric. If you take a multivariable function and you first take the derivative with respect to I, then you take the derivative with respect to j, you will receive the same thing, the same derivative, as if you first took the derivative with respect to j and then with respect to I. So Hicksian demand is, by nature of being a first derivative of another function, satisfies this constraint that it is going to have to be symmetric. So if something is a net substitute, if x is a net substitute for y, then y must be a net substitute for x. And likewise, if x is a net complement for y, y must be a net complement for x. So we have a much nicer sense of what's going on here. So that pretty much covers the lectures on changes in price and changes on income. So we now have under our belt a pretty nice theory of comparative statics in how consumers respond to changes in the parameters of the problem. And that's going to get us very far on the way to starting to describe welfare scenarios, which we'll come back to towards the end of the course.